tooling and machining for the skies, which is the topic today. I have got some conventional ways and innovative, the new generation modern techniques of tooling and machining for the aerospace manufacturing industry, and then later on the innovative perspective. We have got 3D manufacturing, but the topics I'll cover is 3D manufacturing, the CNC machining, automation and robotics, the laser machining, digital twin technology, forecasting potential faults, emerging technologies, and the sustainable processes. Now, the innovative perspective which I have added is aging, the aging of the manufactured parts and assemblies, which normally this uh, this uh, this is a part of the maintenance, predictive maintenance, or you can say preventive maintenance, but this is very crucial and important part. And carry out as we normally do, it should be done like in-depth analysis of all the parts, machines, tooling, and screening. I'll start with the 3D manufacturing first, CNC, laser, digital twin. Now, we, uh, the robotics basically and automation, it gives faster, safer, consistent manufacturing repetitive processes. The repetitive processes like just, they're non-critical processes within the manufacturing techniques, manufacturing industry. This can be carried out by robotics and automation. If you have, if you want top precision, lightweight, high strength materials to be used along with the sensors, we use at AI data analytics along with the CNC and digital twin. So the laser cutting solutions gives fine cuts without mechanical wear, high precision components, and the digital twins, engineers create digital twins for forecasting. Basically, when you create a digital twin, uh, you can go through the background of the material used, the alloys, materials, titanium, whatever the material is used, and the properties of the material can be studied, and a forecasting model for whether there will be a failure after the machining is done, and what is the duration of the usage, basically usage duration. It can be found out by using a digital twin forecasting model. 3D and additive manufacturing, it is a printing is a technique of adding material in successive layers than the conventional cutting of the material and making it high precision. So what we get very complex. If we have a very complex with complex geometries, and we want extreme precision and a lightweight components, so we get it through additive manufacturing. The manufacturing of molds, jigs, and it's fast and cost effective because uh, it cuts down the manufacturing time for the jigs. Allows basically even the material which is normally during the manufacture, which is stuck at the which is normally cohesive, which has a cohesion properties. Usually those cohesion properties are not found in after 3D additive manufacturing is done. So it allows use of sophisticated material like titanium. It of course reduces material wastage and increases accuracy to the level what George described. It reduces manufacturing time and ups the efficiency of the entire system. Now I come to forecasting potential faults and emerging technologies. Sustainability basically is becoming fast one of the top most priorities for every manufacturing industry, including the tooling for aerospace and defense industries. If you want to have a really continuous processes, if we find that the parts manufactured are really accurate, and they are working well, and they're not being replaced frequently at the MROs, then the same part when manufactured in bulk, uh, when manufactured in good volumes, then you can use this digital twin technology, as well as you can use the 3D printing technology. Digital twin technology has the ability to forecast tooling behavior. Basically, it can identify potential faults, improve manufacturing processes. Of course, by incorporating the AI-driven optimization and automation, manufacturers can improve tooling energy efficiency and streamline the operations. Now, very important is how we integrate AI with the AI and automation with the tooling. Uh, that has to become with the data. Basically, when we do the data analytics, it has to come along with the data. So we can integrate along with the tooling and give it to the manufacturers for. Because if we find that is because as I said, sustainability is the key, and preventive maintenance is the key to avoid any potential faults uh, during. So emerging technologies, you can say digital twins and robotics, and to have a really high precision, continuous precision, and repetitive processes. To minimize the potential faults, manufacturers can reuse these digital twin technologies and improve the efficiency and streamline the operations. Now, I come to a very innovative perspective. This is a very it is born out of experience. It is not born out of it is not a conventional mode of detecting faults. Neither is a conventional way of tooling and finding which tools are better for manufacturing during the process, during the any of the manufacturing processes. So aging is a the day one when the aircrafts or satellites or these are used. You use rockets. Day one, it will start deteriorating. Now, which part deteriorates higher? Which parts are continuously forced for a stress and high heat? Uh, those parts will be deteriorating very fast. And what is important is we have to what we feel that we have to find out the average age of all the parts moving or fixed within an aviation ecosystem. So when we find out the age of all the parts which are manufactured, whether it is critical or whether it is fixed, whether it is being used by at MROs or whether it is used at maintenance hangars or the manufacturers, if the average age of the parts are maintained, so we work like this. We work reverse. Um, if we find the average age of the part as for example, 500 hours, then if we are using the same, if we are using the same part um, uh, with the same tooling, we need not, if it is giving average age 500 and if you are expecting average age of 500 or maybe lesser, then we need not go in for very costly toolings and costly machinings. Instead, we can keep the same one. But in case of high stress, high heat, temperature variations, the materials which are aging faster and requires faster replacements. Suppose if the average age of the part is 1,000 hours, then what happens is we feel that it should be changed in a preventive maintenance at 60% of the time used. We don't find this. We have seen that it is overused. Even 1,000 hours, even if this average age, finding an average age is itself a very, it's not a normal technique. At MROs, they have found out that even after 1,000 hours, even if the average is it is average age, it is being used till double the average age. So the properties of the, of course, the properties of the part changes, and then it doesn't give the same, same performance which it is supposed to give. So if we feel that if it is changed just at a preventive maintenance at 60% of the time used, even if it is, even it is, you feel that it is in good condition, it is not. If the average is 1,000 hours, it should be changed at 60% of the time used. And if you mandatorily change at 60% of time used, you can easily, we feel that you can easily avoid the major accidents or major malfunctioning of the parts, engines, or we have seen in recent times some engines getting burned and crashing down. But I don't say that. See, it is if the preventive maintenance is done, very effectively as per this average finding of average age as per the aging of parts, then I think we can avoid lot of accidents. Finding of average age, now it's not an easy task. Finding of average age involves OEMs, manufacturers, and MROs, including consultants who will contribute to their experiences and find out the average age of every part. There's 100,000 lakh, multiple 100,000 parts, but we have to find out the average age because everyone is involved with different parts in this industry. Since it is a $1.7 trillion industry, of course. Every part has got their own set of consultants, and if we find out the average age with the combination of OEM manufacturers, MROs, and the consultants of the relevant manufacturing industry, we can easily avert any major crisis even before we come to know that there is going to be some crisis. So for okay, now okay, I'll just I'll run through this because I'm getting over the time. Over time, aircraft materials like aluminum, steel, composites degrade, which can lead to cracks, fatigue, and corrosion. Older aircraft require more frequent and complex maintenance, leading to significantly higher expenses for operators or MROs. As aircraft age, the components they rely on may no longer be available. Of course, everyone keeps on changing the toolings. They upgrade their even the with the change of the material of the parts, and the toolings are changed. So if the components are no longer available in the supply chain, then it creates a shortage of critical parts. There was a typical example. I'm sorry, I can't name the company of engines, but recently airline went down because of the lack of engines not supplied by the engine manufacturers. Now, there was a dispute, of course, that's why I'm not naming it, but it is evident that there was a shortage of critical parts where the supply chain was incomplete. And now the parts were upgraded. So the old parts were not manufactured. The maintaining, what we suggest is when you manufacture these such critical components, they have to be manufactured and the inventories are to be maintained. Sufficient inventories are to be maintained to last the average age of the entire aircraft, or average age of the parts. So the part manufactured, if the average age is say for example $1,000, and if you expect the part to last for or the aircraft to keep on changing, and the aircraft to last for another 10 years or 10 times. So you can keep 10 parts available on your background. So that's very difficult, but something needs to be done on this, maintaining the inventories for the critical parts, which will not create shortage as we go ahead with new technologies and new materials. And because we want the OEMs to innovate, but if once the OEM innovates, the old parts get out of the system. So maintaining aging aircraft requires higher expertise, upgrading mechanics and engineers to handle unique challenges of older designs. Rigorous and frequent inspections, including NDT, are mandatory. Non-destructive testing mandatory to detect the signs of age-related damage. Now, which is, of course, then it comes under aging. Most important point in aging approach is utilizing the data analytics and condition monitoring to predict failures. I was listening to George that we can utilize data analytics for the of course, then we can predict the failures and optimize the maintenance schedules, and moving from a reactive to a preventive approach then. And yeah, that's all. So this is how I feel that we can avoid major accidents, catastrophes, loss of human lives, and create a very safer aviation ecosystem. Thank you.